All right, so now we're going to talk about going from alkynes to halides to alkynyl halide or alkenyl halides or alkyl halides, right? So let's look at it. Different color. So this is going to look just like you expected. Do you remember this? We add an HX to a halogen, or rather to an alkene, right? It goes like that. And then we get the halide comes in and goes there, right? It makes a carbocation. Well, this is going to be the same thing. So we're going to add an HX, and we're going to get a majority product. We're going to call that good yield. All right, it's not great yield, of course, but we're going to call it good. And so if we add HX to an alkyne, then we can get a vinyl halide, right? The vinyl means it's because it's bonded to a double bond. Right? So, and if we do excess HX, then we get a geminal dihalide. All right. So you might think that this would follow the same mechanism as an alkene, and that would make sense, right? In fact, for a long time, this is the only way I presented this in class as a professor. But this goes here, right? If it was following the same mechanism, this is actually not the correct mechanism, but it's interesting to note this. Watch this. If that went here and this went here, then we would get a carbocation on the vinyl position, right? A vinyl carbocation. And that is really unstable. So this mechanism is unlikely. Moreover, when we study it with kinetics, then we see that we actually get this rate law. Funny, huh? What does that mean? You know what that means? It means that three molecules all collide at the same time. I know. That's amazing, right? 3 molecules collide all at the same time. In other words, it's a third order process, okay? This is not bimolecular or unimolecular, it's termolecular, and we're not going to go into the mechanism. I'm not even going to go into what we think it might be. All right, just want to point out that it's an interesting mechanism. It doesn't go exactly the same as alkenes, but the products are exactly what you would expect. They are the same. Okay, so if we want to do anti-Markovnikov addition, if we want to do anti, then we have to use HBr and a peroxide, just like we did with alkenes. Now, it's important to appreciate this only works with HBr, and we haven't talked about this mechanism, and we're not going to until next chapter. So we're going to get a mixture of E and Z isomers. And so that's, I think, important to appreciate. You can't necessarily say which one that's going to be. Okay? Now, hydrohalogenation of alkynes and elimination of dihalides are complementary reactions, but they just go back and forth, right? If you take this and you add excess HX, then you get a geminal dihalide. Or if you eliminate, right, excess eliminate, then you can get a, you actually have to do this twice. 1, 2, 3 is, again, more of this. And H2O, right? You got to go through 2 steps because it can't happen all at once. But if you write it like that, you'll be fine. Do you understand what I'm saying right here? This is an interesting point. You know what? Take your pencil and paper and try to convince yourself this cannot happen all at once. Show the mechanism. Yeah, we did the mechanism for this, right? This mechanism you need to know. Show the mechanism all the way from here to there and bring it to class. That'd be cool. All right, good luck.